Hey guys, Mr. Milton here. Today we're going to look at substitution notes. At the end of this video, you should be able to solve a system of equations using substitutions. Which method have we already talked about? I already learned for solving a system of equations. That was graphing, right, in the previous video, previous lesson. Okay, what are some of the drawbacks to this method? Okay, intersection of the lines. Okay, what are some of the drawbacks of this method? Intersection of the lines not on the graph. Okay, if our graph is too small to find the intersection of the line, if the intersections of the lines are not at nice points, right? Let's say we have fractional or decimal answers, okay? And had to put both lines in slope-intercept form. Okay, we kind of got around it a little bit with when it fell nice into standard form, but outside of that, we'd have to put in slope-intercept form, and that usually took up a little bit of time for graphing. Okay, so the next method, substitution, takes care of these problems. Okay, and typically, as I talk about the different methods, we will try to stay away from graphing as a method of solving unless the directions say solve by graphing, because the other methods that we'll learn solve it, I think, in a faster way and a more accurate way. Okay, so here we go. Substitution. To solve a system by changing one variable into an equal expression containing the other variable. In other words, instead of two variables, we only have one. Okay, here's the first step. We want to get a variable by itself. Any variable, doesn't matter which one, in at least one of the equations. Okay, so as we look at our first problem, y equals x minus 7, and 2x plus y equals 8. Okay, when we're talking about solving an equation, individually, we cannot solve this top equation just looking at it. Y equals x plus 7, because there's one equation and two variables. Okay, we couldn't solve the second one by itself because there's one equation and two variables. But the beauty of a system is that now we have two equations and two variables. That's enough information for us to solve it. And here's what substitution does. It helps us to use this equal sign. Okay, and I like to think of this equal sign as meaning is the same as, right? Because that's kind of what it means. If I say x equals 2, you know that forever now, like when I say 2, you're saying, oh yeah, that's x. When I say x, you're like, yeah, that's 2. Those are the same things. Those become interchangeable. Okay, and that's what substitution takes advantage of. You say y equals x minus 7. That's like saying y is the same as x minus 7. And that's what our substitution takes advantage of. Okay, so here's our thing. We want to get a variable by itself. This first equation is nice for us. Y is already by itself. We didn't have to do anything to work for that. But then what we do is, since we know y is the same as x minus 7, and we can't solve the second equation with x and y in it, substitution says, well, if you can't solve it with x and y in it, how about we just rename y? 2x plus, notice that y is the same as x minus 7. So instead of saying 2x plus y, I'm going to say 2x plus x minus 7 equals 8. And so, as we have this equation, there's only one variable in it, written multiple times, but it's just x. And so now we can say, okay, 2x plus x, that's 3x, minus 7 equals 8. Add 7 to both sides, 3x equals 15, divide by 3, x equals 5. Okay, I've now found my x, my value for x. Now that I know my value for x, I can solve for y. In my top equation, I am going to now say, okay, y equals, and instead of having to say x minus 7, I can say, well, it's 5 minus 7. 5 minus 7 is negative 2. And so I found x and y, and I can double check that it works just by plugging it into this equation here. 2x, which we said was 5, plus -2 equals 8. 2 times 5, 10, minus 2 equals 8. Does that work? It does. So x is 5, y is -2, and we'll want to write our solution as an ordered pair, 5, -2. All right, second example. This always throws people off because you're like, wait a second, I have two variables that are by themselves. What am I supposed to do? The same thing we did in the previous problem. Once we get a variable by itself, what we can say in the next equation is, okay, x is the same as -2y plus 1. X is the same as y minus 5. Okay, in this next equation, or in either of the equations, instead of writing x, I can substitute -2y plus 1 equals y minus 5. I substituted -2y plus 1 for x. And now I have an equation with just one variable. So as I solve, I'm going to add 2y to both sides. Y1 equals 3y minus 5. Add 5 to both sides. 3y equals 6. Divide by 3. Y equals 2. So y is 2. I can now solve for x by plugging this into either one of the equations. It doesn't matter which one you choose, but I'm going to choose to plug it into this one. So x equals 2 minus 5, right? Because I plugged in 2 for y. So 2 minus 5 is -3. X is -3. Okay, and so my solution should be -3, 2. Okay. Notice that it doesn't matter which values I find first and second. This is a coordinate, and so it goes x, comma, y. X, comma, y. All right, next problem. So a little bit more challenging here because in our first two problems, we had a variable by itself, right? Y was by itself in the first problem, and in the second problem, x was by itself in both equations. But here in this example, we don't have a variable by itself, so we have to add to this problem, which variable is easiest to get by itself. So as I look, x, 4y, 3x, -2y, it appears that x is going to be the easiest to get by itself. And I can get it by itself in this top equation by subtracting 4y from both sides. And so I have x equals -4y plus 11. X is now by itself. Now that I have this variable by itself, I'm going to substitute it into the second equation so that I only have one variable there. So I'm going to rewrite the second equation as 3 times -4y plus 11 minus 2y equals 19. Notice that everything else in the problem stayed the same except the substitution part. I changed x to -4y plus 11 because I've already seen that those are the same things. And now I go and solve. So I got -12y plus 33 minus 2y equals 19. Combine my like terms. These are on the same side, so I just combine them. That's -14y plus 33 equals 19. I subtract 33 from both sides, and that gives me -14y equals -14. Divide by -14, I find that y is 1. All right, and now that I know that y is 1, I can plug it into either one of these equations to find x. Okay, and so I'm going to plug it into the top equation because I think it's easiest. And so I have x plus 4 times 1 equals 11. X plus 4 equals 11. Subtract 4 from both sides. X equals 7. So y is 1, x is 7. I could plug it in to make sure it works out. Here's my ordered pair. Next one. Okay, again, another problem where we don't have anything by itself. We would say, okay, what's going to be the easiest to get by itself? Okay, and now as I look at these problems, 5x, -y, x plus 2y, looks like this x is going to be the easiest to get by itself. It's already no coefficient or number by it, and it's already positive. Okay, and so to get x by itself, I'm just going to subtract 2y from both sides. And so I could rewrite this as x equals negative 2y plus 16. And this is nice because now in my first equation, instead of writing 5x, I'm going to write 5 and then substitute for x, negative 2y plus 16. Minus y equals 47. Distribute gives me negative 10y plus 80 minus y equals 47. Combine my like terms, gives me negative 11y plus 80 equals 47. Subtract 80 from both sides, negative 11y. So 33, negative 33. Okay, divide by negative 11, and I find that y is 3. Okay, now that I know that y is 3, I'm going to plug it into either of these equations. I'm going to choose the second one because that's where x is by itself. I'll say, okay, x plus 2y equals 16. So x plus 6 equals 16. Subtract 6, x equals 10. And so I have my solution as 10, 3. All right, up here, let's look at some special cases here. First equation, we have 6x plus y equals 10 and y equals negative 6x plus 1. This second equation, we already have y by itself, so I don't need to move anything around to get it there. So now I'm going to substitute that into my first equation and rewrite it. 6x plus negative 6x plus 1 equals 10. Combine my like terms. 1 equals 10. My variables are gone. There's no more variables. I have 1 equals 10. It's not true. Remember, we've seen something like this before, and that was a sign that there was no solution. Okay, no variables in an untrue statement tells us there's no solution. If there's no solution, remember, in our system of equations, that means that these lines would be parallel. Right? That means the lines that would be created here don't intersect. We saw that last chapter with our special cases. So in our second example, we have 2x plus 4y equals 8 and x equals negative 2y plus 4, right? And so I already noticed that my x is alone in the second equation. And so what I can do then is I can say x is the same as negative 2y plus 4. In my first equation, that's going to help me out. Okay, I'm going to rewrite this first equation as 2 times, and instead of using x, I can say, well, it's negative 2y plus 4. It's the same as x. Plus 4y equals 8. Okay, and so I distribute over here, gives me negative 4y plus 8 plus 4y equals 8. Combine my like terms, right there on the same side, but that gives me 0. And I have a true statement with no variables. 8 equals 8. So there's infinitely many solutions. These lines would be coinciding or the same. Okay, these two examples are special cases, just like the ones we looked at with graphing, since in both examples the variable cancels out. So how can you tell the difference between no solutions and infinitely many solutions? Remember that no solutions, the variables cancel out and the remaining numbers are not equal. And infinitely many solutions, the variables cancel out and the remaining numbers are equal. Okay, and that is solving systems by substitution. See ya.